All right, BC kids, here comes the first section of Unit 16. There's only 3 sections, but this is on parametric equations, and you probably have never seen these before. But it's kind of interesting because you can represent, this is just a ball that's thrown in the air. So here you are, you throw a ball in the air. All 3 of these graphs are graphs that deal with the ball being thrown in the air. One is the vertical distance over time. One is representing the horizontal distance over time. And the last one is looking at the horizontal distance versus the vertical distance. So different representations that you can take, all from one ball being thrown in the air. So until now you've been representing a graph by a single equation involving 2 variables, are normally x and y. In this section, we look at situations in which 3 variables are used to represent a curve in a plane. Consider the graphs below. Each one models different aspects of what happens when an object is thrown in the air. I said a ball. Okay. The graph on the left shows the vertical distance the object travels as a function of time. The middle graph shows the object's horizontal distance as a function of time. The graph on the right shows the object's vertical distance as a function of its horizontal distance. Each of these graphs and their equations tell part of what is happening in this situation, but not the whole story. To express the position of the object, both horizontally and vertically, we can use parametric equations. The equations below both represent the graph shown on the right. So in a rectangular world, in our normal Cartesian world, this is what it would look like, y equals. And you can see, yeah, it's a parabola. It's an unhappy parabola. It kind of makes sense, right? In the parametric world, you have 2 separate equations, one for x and one for y, and they're all based off of t. Now t in this case is time. T is time, and it's your parameter. Time and, well, time is the, I'll put time is the parameter. That's what makes them parametric equations. You end up with a separate equation for x than you do for y, and it's all based off of t being your variable for time. You'll see this more as we do more examples. From the parametric equations, we can now determine where the object was at a given time by evaluating the horizontal and vertical components. For example, if t equals 0, the object was at 0, 40. If I put a 0 into here, I get 0 out. If I put a 0 into this equation, I get 40 out. And so you can figure out what the x value and what the y value would be as a coordinate. So 0, 40. The variable t is called the parameter. We just talked about that. The graph shown is plotted over the time interval from 0 to 4. Plotting points in order of increasing values of t traces the curve in a specific direction called the orientation of the curve. This orientation is indicated by arrows on the curve, and I don't know that you can see them very well, but if you look closely, it starts out with a t of 0 is at 40. If I put a 1 in, I get here, I get 4260, but you'll see there's a little arrow right in there to say it went in that direction. And then there's an arrow here to get to the next point. And then there's another arrow to tell you to get to the next point. And so you use arrows to show the directional value of this. It might be a little like physics. I don't know if any of you have had physics, but you might have seen these before in that kind of an environment. So without a calculator, make a table and sketch the curve indicating the direction of your graph. So this is example 1. I have an x equation and I have a y equation. They're both in terms of t, and my t values are between -2 and 3. So what I do is I set up a table of values. T, x, and y. Seems strange to have 3 columns, but that's what we have. All right, t starts at -2, right? So I'm going to use -2, and then I'm going to complete the table. I'm going to keep going until I get to 3. And I'm just going to use the whole numbers. -2, -1, 0, 1, 2, and 3. All right, so what I'm going to do then is plug them into the formulas they give me for x. Well, this formula is t squared minus 4, and the y formula is t over 2. All right, if t is -2, -2 squared minus 4 is 0. If t is negative 2 over 2 is a negative 1. And what I'm going to do is, for the sake of time, this is a really long section, so for the sake of time, I'm just going to tell you what these values are. So, and again, all you're doing is plugging the value of t into these two equations. So you get negative 3 gives you negative 1/2, 0 gives you negative 4, 0, 1 gives you negative 3, 1/2, 2 gives you 0, 1, and 3 gives you 5, 3/2. And what you do is you come over here to your graph and you start where you're supposed to start, negative 2, and you plot the coordinate. You're in the XY Cartesian coordinate plane, and so all you're doing is plotting points, 0, negative 1. Okay, 0, negative 1. Here's where it starts, right at that coordinate right there. This is when t equals negative 2. And then the next one you come to is negative 3, negative 1/2. Negative 3, negative 1/2 would be right here. This is t equals negative 1. You connect them together and you put an arrow on it saying that's the direction it went. Next coordinate is negative 4, 0. That's here. And that's when t equals 0. And again, I'm going in this direction. If I go negative 3, positive 1/2, negative 3, positive 1/2 is here. That's when t is 1. By the way, you don't have to put all these t values on there when you really are graphing. I'm just doing it this time to show you the movement of this thing. And then the next point is 0, 1. That's here. Arrows. That's when t is 2. And for whatever reason, when these people made this this packet of notes, they stopped there, but I don't know why, because you're supposed to stop at 3. So I'm going to go one more to 3. If I have, that would be 5. Now maybe that's why they did, because it goes off the graph, right? 4, 5, and then I have a value of 3/2. So that would be approximately here. This will be when t equals 3. I want to connect those guys together and put my arrow. Now it's a smooth thing. I'm a little bit crooked there, but you get the idea. So did we answer the question? Without a calculator, make a table and sketch the curve, indicating the direction of your graph. Yep, got it done. All right, flip. That's the idea of a parametric function. So finding a rectangular equation that represents the graph of a set of parametric functions is called eliminating the parameter. In other words, you're getting rid of the t. So it basically means that you solve one equation for t and plug in the other equation, giving you an equation in terms of only x and y. Does that make any sense? You'll see it. It makes a whole lot of sense. It's pretty relatively easy. So you have to choose. You're either picking this guy to solve for t or this guy to solve for t. Obviously, the y guy is the easier one, so that's what I'm going to do. If I have y equals t over 2 and I want to solve that for t, what am I going to do with that 2 to get rid of it? And you say you're going to multiply. So t equals 2y. And then you do a direct substitution. So you substitute. That's your deal. Substitute that into the other equation. So it's going to be x equals, not t, 2y squared minus 4. And then you can solve it out. So you get x equals 2y times 2y is 4y squared minus 4. And then the last thing you do is, normally we see our equation solved for y, and that's what we're going to do. So I'm going to make this, a lot of different ways you can do this, but 4y squared equals x plus 4. I can take that 4 and divide it. Y squared equals x plus 4 all over 4. And then to get y by itself, I have to square root it. So I'm going to square root both sides. And that gives me y equals plus or minus the square root of x plus 4 over 4. Now just for kicks and giggles, here's what the book answer was, which is an equivalent answer. I'm going to change my color so you can see the difference. Here's what they said. They said it's 1/4 x plus 1. And they're right, and so are we. We're saying the same thing, just a different way. So the only reason I bring that up is sometimes you could see that on a multiple choice question, and it might be in this format or it might be in that format, but they're one and the same. X over 4 is 1/4 x, 4 over 4 is 1. Okay, so then they say, all right, check it by graphing it, and this is pretty cool on your calculator. Let me see if I can make sure that you can see what I've got going on here. Okay, first thing you need to do to graph a parametric equation is put your mode into parametric. So if you hit the mode button, the very first thing you see is function. If you go to the right, you have all these choices. For this particular section, I'm looking at parametrics, right? So get down and highlight number 2. Press enter twice. All right, go to your y equals. In your y equals, you're going to put in your x. See how it has an xt1 and a yt1? Your xt1 is going to be, and you literally have a t button. Your t button is next to the z, next to the caret. So t squared minus 4. And then go to your y t1 and put in t over 2. All right, there you go. Then you're going to graph it. Here it is. Hit the graph button. Yeah. And it's not happy. Oh, you know why? Because I did this when I was practicing it too. Somehow or other I went into the YT2 instead. So let me change this up. I got to clear myself out. I'm out of the loop. All right, hopefully you did better than I did. T squared minus 4, and then I have t over 2. All right, that should be better. Let's try graphing it now. When nothing shows up, you know that there's an issue. Now, you might need to change the window, right? Because if I look at this, this doesn't necessarily show me all that this thing does. So if I change my window, remember my my t has to be between -2 and +3. My t min, is going to be -2. And my, oh, not 22. Good Lord. -2. And my Tmax has to be 3. Now if I do that, and I don't care about the rest of it, and graph it, that should give me the exact picture of what I've got, which is what I have. There you go. All right, so the next question says, all right, graph this, try this. X is 4t squared minus 4, and y equals t. Go back to your functions, clear out what you got. Putting in a 4t squared minus 4 for my x, and I'm putting in a t, just a regular old t, for my y. And then before I graph it, I'm going to change my window. They say, okay, go between -1 and 1.5. Hit the graph button. Now you say, wait a minute, look at that. What do you notice about that? That's exactly the same graph as what you have from example 2. So it's the same graph as above, but the equations are entirely different, and your window for t is entirely different. So it turns out that this is the same representation as above. These are all equivalent. They give you the same graph when you put them out, when you put them in the calculator. When you go and graph the points, you're going to get the same values. So it's the same as above. And again, for sake of time, if you put in this guy with the trig functions, believe it or not, he's going to be the same thing. If you put your t factors in as -1.571 to 0.253, all of 3 of these graphs come out to be the same exact picture, although they are all different representations, which is kind of interesting. So the point is that you can have the same graph, but have it represented by totally different functions and totally different windows. All right, example 3. This one says, make a table and sketch the curve represented by the following parametric equations. So I have two equations, an x equation, a y equation, and they told me that t is greater than -1. Now if it's greater than -1, that means it's not equal to. Take note of that. They're not saying it's equal to. So when I go to make my table of values, which is what they asked me to do first, I have a t value that I'm starting with, I have an x value and a y value. So for this one, I'm going to start with, I can't start with -1. I'm going to start with, actually maybe I should, even though it doesn't exist. So maybe we'll put in -0.999. Something close to -1. If I do that in my calculator, let's see. I have a t plus 1 to the 0.5, actually -0.5 power. And there we go. And I have a t divided by t plus 1. There we go. All right, so if I put that in there, I'm going to go to my table just so it saves me some time here. So look at the table. This is pretty cool. If I put in a -0.999, what is my calculator issue today? -0.999. It gives me 31.623, 31.6 for x. And it gives me a y that's -999. Holy guacamole, we're going to look at that in a minute because I ain't graphing that. That point is not plottable. But since I have this in here, I can get my other table values pretty easily. Now you're going to pick numbers that are nice for t, right? So if I pick, say I pick 1, I get 1 over the square root of 2. That's not nice. But if I pick t equals 0, that's going to give me the square root of 1, which is 1. So my next nice t value is when t equals 0 gives me an x that's 1, and this gives me a y that is, if t is 0, I get a y value of 0. 0 over 1, and so there you go. So again, for sake of time, the next one I picked was 3. And you can put this in your calculator again in the table. Say I put a 3 in. Oh, not positive 3. If I do a 3, it gives me 0.5, I'm sorry, 0.5 and 0.75, that's true. So 3 gives me, and you can put it as fractions or decimals. 3 gives me a half and 3/4. The next nice one is 8. 8 gives me 1/3 and 8/9. And so I'm going to plot those points, x's and y's. Now I'm not going to plot that first one quite yet. We'll talk about him in a minute. I have a point that's at 1, 0. And then it goes to 3. At 3, it gives me 1/2. 1/2. Here's 1/2 going this way. 3/4. So I'm kind of in this neighborhood. When I connect them together, remember I'm putting a direction to them. And then 1/3 is a little bit smaller than that. That's up here really close to the y-axis, and that gives me an 8/9, which is pretty small. I don't know that I've got room in there to put an arrow, but you kind of, I guess you could. And then I've got this crazy one. When x is 31.6, y is -999. So in other words, this thing comes down like this and keeps going. I can't use -1 directly because -1 is not equal to, but I can come somewhere close to it and see what it's doing in that direction. So this one actually does go down to -infinity. All right, eliminate the parameter in the parametric equation above, verify on your calculator. So if I were to choose which one I'm going to solve for t, that's really your deal first, is solve for t, and then you're substituting and then you're solving for y. That's your plan. That's the game plan when you're trying to get rid of the parameter, eliminate the parameter. So take one of the equations, solve for t. I don't want to mess with that square root. That would be a hot mess. Or actually I do. Maybe that's easier because this one has two t's in it. Now that I look at it, this only has one t. So I'm going to go with this guy. I'm going to start with x equals 1 over the square root of t plus 1. So again, I don't like the square root, so how can I get rid of it? And you say, square both sides. If I square both sides, here I am. And then you know me, I'm a big fan of cross multiplying. That's going to give me x squared times t plus 1 equals 1. And remember, I'm trying to dig towards the t. So I'm going to get rid of this x squared. So it's going to, my next step is going to be t plus 1 equals 1 over x squared when I divide it, so that t equals 1 over x squared plus minus 1. Swinging that 1 over. All right. Now that's solving for t. Now I got to substitute it into the other guy. And you're like, what is that going to be? So here you go. You're going to have that y equals t 1 over x squared minus 1 over t plus 1. 1 over x squared minus 1 plus 1. Well, obviously the negative one and the positive one cancel each other out. And so what I really have, I'm going to go horizontal here, is 1 over x squared minus 1 being divided by 1 over x squared. So in this first set of parentheses, if I get a common denominator, my common denominator is x squared. This will make it 1 minus x squared. Right? This would have to be x squared over x squared to be 1. And if I'm dividing by 1 over x squared, keep, change, flip, I'm actually multiplying by x squared over 1, cancel, cancel. And so I get a final answer that says y equals, remember I just solved for y. Maybe I didn't finish that, solve for y. Solve for y, I get 1 minus x squared. Now look at the graph. Does that at all fit? Does that kind of look like a 1 minus x squared situation? And you say, yeah, it's an unhappy parabola moved up 1. Except it's only half of it because remember we had a parameter here that told us that our t values can only be greater than -1. So we're not looking at the entire graph, we're only looking at part of the graph. But this certainly mirrors that same function in the t world, parametric world, versus the rectangular world of x's and y's. All right, so we're ready for the next example, and this one involves trig functions, your favorite. Example 4. This one also says make a table of values and sketch the curve represented by the function of parametric equations. And there you go. Now I'm making my table of values. How does it work? I take t values and I take x values and I take y values and I make a table of values. Now if they ask you, and I'm going to put this up above, if they ask you about trig functions, notice this one didn't say going from like -2 to 3 or going from t is greater than -1. If they don't tell you with trig functions, use t values that are pretty. Like what are some pretty values in the trig world? You start at 0, you go to pi over 2, then you go to pi, and then you go to 3 pi over 2, and then you go to 2 pi, and you could keep going, but they're the pretty ones, right? And that's what we're going to do. We're going to do exactly the same thing. They didn't tell us anything, so we're going to use those, and here I go. So if it's t is 0, and again for sake of time, let me do the first one anyway though. If I put a 0 in for my angle, cosine is 0. Well, cosine is 0 is the coordinate 1, 0. That means that cosine, it would be 1, it's the x coordinate. 3 times 1 is 3, plus 2 more is 5. If I go for putting it in here, 0, sine of 0 is the coordinate 1, 0. It's the y value of 0. 2 times 0 is 0, and 0 times plus a -1 is -1. So there's your first one. And then you're doing the same thing at pi over 2. That's my next guy. You're doing the same thing at pi. at 3 pi over 2 and at 2 pi. And when you plug in those values and go around your unit circle and get those coordinates, here's what your chart looks like. 2, 1, negative 1, negative 1, 2, negative 3, and 5, negative 1. And again, it's just direct substitution into those equations, but you need to know your unit circle to do that. So let's plot them. And again, I'm plotting the xy part, so 5, negative 1 puts me here. That's my beginning place. And then I go to 2, 1. Well, 2, 1 is here. So when I connect them, by the way, these are normally a little curvy. Well, you could put a straight line to them, but they're definitely not pointy. These are curvy kind of graphs. Next one is negative 1, negative 1. Actually, did I do that one wrong? I did. 2. Negative 1 is down here. There's an issue. Actually, it's my curve that's the issue. All right. All right, I have, let me try this again. As I connect these two together, they don't curve that way, they curve this way. That's me. All right, and then I go to this guy. It makes more sense. They shouldn't be pointy. Did you see I would have had like a cusp looking thing if I had curved it the other way? So anyway, that's why I knew I was wrong, because it shouldn't have any pointy places. 2, negative 3 puts me down here. Right, so I'm now at this point, going to this point, put your arrow on, and then actually 5, negative 1 goes back and closes it up. So you kind of end up with this ovally looking thing. But did we answer their question? Make a table and sketch the values. Sketch the curve represented. We did. And then they say, okay, now eliminate the parameters. So I've got to take one of these equations and I've got to solve it for x and then substitute it in. You can see it's going to be a nightmare with trig functions. So there's a trick with trig functions. Watch and see what happens. If I take this thing and I solve for, I'm going to take my first equation. My first equation is my x equation, and it says 2 plus the cosine of t. If I solve it for the cosine of t, what would that look like? Actually, this is a 3 cosine of t, right? 3. So if I take this and move the 2 over, I've got x minus 2. But I want to know what the cosine of t is. So it's going to be x minus 2 all over 3. I'm going to do the same thing with the y equation. I'm going to solve for the sine of t in that case. Y equals negative 1 plus 2 sine of t. Take that guy, solve it for 2 sine of t. Gives me y plus 1. And that means the sine of t equals y plus 1 over 2. All right, put your trig pants on. Pull out that toolbox of trig things that you know. And see if you remember something about sines and cosines, like this. Sine squared t plus the cosine squared t equals, do you remember this guy? This Pythagorean relationship equals 1. Right? So you got to go back and see if you can remember. And this only comes up when you see sines and cosines, because there's no way for you to put them into the rectangular world other than to go back into those trig identities and do it this way. So what do you know the sine is? You know the sine of t is y plus 1 over 2, quantity squared, sine squared, plus cosine squared, x minus 2 over 3, quantity squared, equals 1. And then sometimes you might see it written this way. You might see it written as y plus 1 over 2, squared over 2 squared, which is 4, plus x minus 2 quantity squared over 9 equals 1. Equivalent forms again. Sometimes this is the more popular one because it goes with conic sections, which is what really this is a picture of, is an ellipse. So from this equation, you can tell what where the center is and all that kind of stuff that we're not going to talk about, but that's the equation. So sines and cosines revert back to the Pythagorean theorem, and that'll be helpful to you. So next thing is, can you take derivatives of these equations? And sure you can. So here comes the calculus. I'm going to tell you that dy over dx equals dy over dt over dx over dt. And then if I want the second derivative, what I need to do is take the derivative of this and divide it by dx over dt. And you're saying, what on earth is all that? And he tried to explain it in words down here. But again, we're going to go into examples and see how to actually apply it. To find the first derivative, find the derivative of y with respect to t and divide it by the derivative of x with respect to t. Derivative of y divided by the derivative of x. To find the second derivative, take the derivative of the first derivative with respect to t and divide it by the derivative of x with respect to t. So this is kind of his wording of how to do it. It's actually not bad. It's not bad. But I'm going to show you in examples how to make this thing happen. So if we flip the page, there are an endless number of examples in this section. I'm trying to go as fast as I can without losing you. All right, given that x equals 2 square root of t and y is 3t squared minus 2t, find the first derivative, dy over dx, and the second derivative, d squared y over dx squared, and evaluate it for t equals 1. All right, so first job number 1 is to find the first derivative, dy over dx. All right, that's what we're going to do first. Well, that's the same thing as finding y prime and x prime, right? I've got y prime, so I'm going to start with y prime because that's my dy over dt. My y prime is going to be 3t squared minus 2, so I'm going to take the derivative of that, and I get 6t minus 2. Then I got to find my x prime. I don't know that I want an arrow with this because it doesn't just equal that piece. X prime. Now this guy here, if I'm thinking about taking a derivative, he's 2x to the 1/2 power. That helps me a little bit myself to be able to see what it's going to be. And so, derivative of that, the 1/2 comes down, multiplies by the 2, they cancel each other out, and I just get x to the negative 1/2. Or, I'm sorry, no, it's t, right? T to the negative 1/2. T is my variable. 1 over the square root of t. And then here's what this guy really means. This guy says to find the derivative, take y prime and divide it by x prime. All right, let's do that. So I have dy over dx is going to equal y prime divided by x prime, 6t minus 2 divided by 1 over the square root of x. Now what happens when you divide by that fraction? Keep, change, flip, multiply by the reciprocal. And so my final best answer for this derivative is going to be 6t minus 2 times the square root of x, or t. Why am I putting x's? Because I'm all x obsessed. 6. Oh, and 6, right? Jeez Louise. T. I think that's what happens when I try to work fast. I end up talking in circles. All right, there you go. That's your answer. That's your first derivative. Job number 2, they want us to find the second one. So this is my d squared y, and again, maybe my zoom is too big, but d squared y over dx squared. That's my second step. Well, there's 2 pieces involved with this. This one's going to be the derivative of this guy, dy over dx, the answer you just got, and you're dividing it by x prime. That's the deal. That's what all that gobbledygook on the other side said. So, if I take the derivative of this one, now There's a couple different ways you could do this. You could definitely do it by doing the product rule if you wanted to. I'm just going to distribute the fact that I know that this is a t to the 1/2. So 6t times t to the 1/2, and this, I'm not ready to derivative yet. I'm just setting it up so I can derivative. So if I look at this guy, he's 6t times t to the 1/2, that gives me 6t, 1 plus 1/2 is 3/2. 2 times t to the 1/2 is minus 2t to the 1/2. And that's what I'm going to use to take the derivative, because that's going to make my life a little bit easier. So, taking the derivative of dy over dx, the 3/2 comes down in front. So that's going to be 6 times 3/2 t to the 1/2. Right? Take it to 1 less power. Minus 2 times, bring the power down, 1/2 t to 1 less power, negative 1/2. And that's going to be over. Now I've got some simplifying to do there for sure. That's going to be over this t to the negative 1/2. And again, you could put it as 1 over the square root of t, but you'll see why I don't do that in just a minute. All right, I'm still working on this. Let's see if we can simplify a little better. I have 18 over 2 is 9t to the 1/2. I have 2 times 1/2, they cancel, so minus t to the negative 1/2 over t to the negative 1/2. And then I can divide this up as a single monomial denominator, so I can put them separately to get over each other here. Watch and see. 9t to the 1/2 over t to the negative 1/2 minus t to the negative 1/2 over t to the negative 1/2. Can I make it better? Sure you can. All right, what happens with my powers when you're dividing? You subtract them, right? So you end up with t, the 9 stays 9. You got a 9. 1/2 minus a negative 1/2. 1/2 minus a negative 1/2 gives me just a t to the first. And t to the negative 1/2 over t to the negative 1/2, well, that's just a 1. And so that, my friends, is what d squared y over dx squared actually equals your second derivative. So it's the derivative of dy over dx, the first derivative, divided by x prime. All right, here comes the next one. For this one, again, we're back to trig functions. Given that x equals 4 cosine of t and y is 3 sine of t, write an equation for a tangent line to the curve at the point where t is 3 pi over 4. So we know if we want a tangent line, we need two things. We need a point and we need a slope. Well, let's start with a point first. I have an x coordinate that is 4 cosine of t, and I have a y coordinate that is 3 sine of t. Well, do you know what t is? Yeah, it's 3 pi over 4. So 4 cosine of 3 pi over 4 equals, and this guy's going to be equal to 3 sine of 3 pi over 4. So I go around the unit circle, and 3 pi over 4 gives me the coordinate. Let's see, it would be a negative square root of 2 over 2 and a positive square root of 2 over 2. That would be the coordinate. Again, Mr. AP assumes that you know that in your head. All right. Well, cosine is the x value, so I'm going to have 4 times negative square root of 2 over 2. That gives me a negative 2 square root of 2, right? 4 times the 4 and 2 cancel. It's negative 2 square root of 2. This one gives me 3 times a positive square root of 2 over 2. That's going to be 3 square root of 2 over 2. There's your point. So the point for our tangent line is negative 2 square root of 2, comma, 3 square root of 2 over 2, and yeah, you can kind of see me there. There's my point. Here's my slope. Well, the slope is going to be y prime over x prime, right? It's going to be the derivative of y over x. So, go to your y equation and find the derivative. That's going to be 3, derivative of sine is cosine of t. This guy's going to be the x it's going to be negative sine, right? So it's 4 negative sine of t. I'm going to put the negative in front. But I want to know what it is when I evaluate that at 3 pi over 4. I need to know a number for the slope. So it's going to be 3 cosine of 3 pi over 4 over negative 4 sine of 3 pi over 4. Plug in your values from the coordinate. 3 cosine is the x, negative square root of 2 over 2. Negative 4, the sine is the y, square root of 2 over 2. I have up top a negative 3 square root of 2 over 2. And on the bottom, I have a negative 2 square root of 2. Now the negative cancel. So what I really have is, remember I'm trying to get to a number because this is the slope. 3 square root of 2 over 2 divided by times 2 square root of 2 over 1. Right, you take and divide, so you're multiplied by the reciprocal. And so here's what I've got. 2's cancel. 3 times the square root of 4 is 3 times 2. That gives me not the slope I wanted. Hold on. All right, let me go back a step. I'm trying to cut corners and it's not working. All right, divided by, let me do it this way. 2 square root of 2. That's better. If it's dividing by, so 3 square root of 2 over 2 divided by 2 square root of 2. Again, the negative over negative became positive. And so now let me try keep, change, flip. 3 square root of 2 over 2 times 1 over 2 square root of 2. The square root of 2's cancel. 2 times 2 is 4. That's better. 3/4. So now that you have all your info, can you put together the equation of the tangent line? You've got your slope, you've got your point, and so you're going to just toss that together and call it a tangent. So tangent is y minus 3 square roots of 2 over 2 equals your slope of 3/4, and you've got x minus a negative, so plus 2 square root of 2. And there's the equation for your tangent line. So you got to find the point and find the slope, and that's your story. All right, flipping again. Example 7. Find all the points of horizontal and vertical tangency. That's such a mathematical thing. Given that x equals t squared plus t and y is t squared minus 3t plus 5. Well, let's just talk in general first. If I have a horizontal tangent line, think about what the slope is. Right, horizontal tangent lines, no rise, no run, slope is 0. Now in our world today, with what we're looking at, that means that I need to know when y prime over x prime, when my derivative is equal to 0. Now if I have a vertical tangent, that's when my slope is undefined. Undefined. Now think of your fraction here. When is that fraction undefined? And you say when the denominator equals 0. So when x prime equals 0. So that's what you're looking for. These are two totally separate problems. You're looking for, first thing, when the derivative equals 0, that's going to tell you horizontal. When x prime, the denominator, equals 0, that's going to give you your verticals. So let's figure out what they are. I need to know what x prime is, and I need to know what y prime is, and then I can put all these pieces together. X prime is going to be 2t plus 1. Y prime is going to be 2t minus 3. All right, well, they're pretty. They're not bad, right? So if I'm looking for horizontal, I'm doing y prime over x prime. Here it is. Y prime is 2t minus 3. X prime is 2t plus 1. I'm going to set that equal to 0. Well, it's kind of like 0 over 1, and when I cross multiply, I'm left with just what the numerator is. So really what I want to know is when's 2t minus 3 equals 0? That's when t equals 3/2. And you think you're done the problem, and you're not. And here's the issue. Look at the directions again. Find all points. In other words, I need an x value and a y value. Points are x's and y's. They're not t values. So what I need to do is then go back to my equations and fill in the t that I got so I can figure out what the coordinate is for that point. And so it's going to be, if I actually change my color, it's going to be that x equals t squared, 3/2 squared plus 3/2. Right, I'm just putting it right into that equation right there. And again, for sake of time, I'm going to tell you that this comes out to 15/4. My y value is going to be, put it in here, 3/2 squared minus 3 times 3/2 plus 5 equals, and again, it gives you 11/4. So I have a coordinate for the horizontal that's going to be, where I'm going to have a horizontal tangent line, 15/4, comma 11/4, x's and y's. I so want to box that in, but I'm not going to box it in. All right, here we go, vertical. Vertical is when x prime, my denominator of my slope, equals 0. So what is x prime? X prime is 2t plus 1. Well, 2t plus 1 equals 0 when t is negative 1/2. Swing the 1 over, divide by 2. Then you're going to do the same thing. You need the coordinate where that happens. So my x is going to be negative 1/2 squared plus a negative 1/2. That gives you negative 1/4. My y is going to be negative 1/2 squared minus 3 times negative 1/2 plus 5. And that's going to be a value of 27/4. So my coordinate for this one, where it's a vertical tangent, is going to be negative 1/4 and 27/4. And that's the answer to the problem. So really, this is classic. This is a classic one. I've seen it before on the exam, because you got to kind of do a lot of, it's not that hard a problem, but you got to do a little bit of thinking to figure out, well, where is it horizontal and where is it vertical and what does that mean? But that's your deal. Then they get into parametric arc length. In other words, if you want to figure out how far it is from one coordinate to the next, or how far it is for a certain portion of your parametric curve. And so here they gave you the formula. It's pretty simple. The length is the integral from a to b of the square root of x prime squared plus y prime squared with respect to t. And so pretty easy setting it up. These are totally calculator problems. So x prime equals, take the derivative. Well, the derivative of t squared is 2t. Y prime derivative is 12t squared. So I'm going to set it up. My arc length equals the integral from 0 to 1, they said. Okay, 0 to 1. Big old square root x prime squared, 2t squared, plus y prime 12t squared, squared, with respect to t. And so what you're going to do is go into your calculator and literally figure out that integral. Now, I'm not going to go into the calculator and necessarily do that. I'm going to tell you the answer again because I don't want this to be a 2-hour video. One thing I do want to alert you to is when you're done in the mode of parametrics, make sure you change it back to function because that's what we do the majority of the time. So I'm going to change mine back to function while I'm thinking about it. All right, there it is. And then you're just going to go in and find the regular old integral the same way you always do. Now, could we do this by hand? Absolutely we could. But we're going to do these with calculators, and the answer is 4.149. It's an approximation because you're rounding. So you can use the squiggles. That, you know, Mr. AP kind of prefers that in the midst of a question like that. All right, we're winding it down. We're almost done. Here comes the next page. Now they give you a pretty box, and it's a pretty box because they're trying to tell you what these different things mean and put all the formulas in one place. So all the things we talked about in the section so far are in this pretty little box. x prime of t is the same thing as dx over dt, and it's the rate at which the x coordinate is changing with respect to t. Or it could also be the velocity of the object in a horizontal direction. Y prime of t is dy over dt. It's the rate for which the y coordinate is changing with respect to t, or the velocity of the object is moving in a vertical direction. X of t, y of t is the position. That's just the regular old coordinate for time. If I have the first derivative, that's velocity. That doesn't change. If I have the second derivative, that's acceleration. Same thing that we've always talked about. Dy over dx. Notice that's different than dy over dt. Dy over dx is the rate of change of y with respect to x, or the slope of the tangent line. That's what we just were doing. D squared y over dx squared is the rate of change of the slope of the curve, like the second derivative. Speed is this square root. It's just the square root part, not the integral part, and distance is the integral part. All right, example number 9. I think this is the last one. It is, but it's got 4 parts. This is a classic AP exam type question because it's asking you all sorts of different things by just giving you 2 equations here for an x equation and a y equation. Let's see if we can handle it. It also kind of summarizes everything that we've been doing in this section. So you've got a particle that's moving in the xy plane. Those particles, they're something. T is greater than or equal to 0. The position of the particle is given by x equals yada and y equals yada. Find the parametric equations representing the velocity of the particle, and then find the horizontal and vertical components of the velocity at t equals 1. Well, let's talk velocity, right? V of t. We'll go back up to your pretty little box here, and in the pretty little box it says, okay, well, velocity, here it is x prime of t comma y prime of t. All right, so let's figure that out. Equals, I'm going to put it right here just so that we can see it, x prime of t comma y prime of t. Well, what are they? Can we figure them out quick? X prime of t, 3t squared plus 8t. All right, then I'm going for y prime of t. Well, y prime of t is going to be 4t cubed minus 3t squared. 4t cubed minus 3t squared. Then find the horizontal and vertical components of the velocity at t equals 1. So here's what they want me to do now. They want me to figure out what v of 1 is. Well, all I need to do is plug a 1 into that equation. And when I do that, I get 3 times 1 squared is 3. 8 times 1 is 8. 4 times 1 cubed is 4. Minus 3 times 1 squared is 3. Well, here's your horizontal, 11, and here's your vertical movement for that particle. Find the horizontal and vertical components. They're your components. You got a horizontal, you got a vertical. Okay. B, find the speed of the particle at t equals 1. Well, speed, right here, there's your formula. It's like your golden formula sheet there. Dx over dt is like x prime squared, and dy over dt is like y prime squared. So that's my speed. Speed equals this lovely square root. Well, didn't you just do the work right up here for this? So I'm going to do it the long way, but you'll see that there's really a shortcut to this in just a second. If I take the derivative of x, 3t squared plus 8t, and square it, add it with the derivative of y, 4t cubed minus 3t squared, and square it, I want to know what it's doing at 1 again, t equals 1. Well, didn't you calculate that already? This is really the square root. When I put a 1 into this, it was 11 squared. When I put a 1 into this, I got a 1 out. And what's 11 squared plus 1 squared? And you say the square root of 122. And that's it. That was that one. So again, they're not crazy hard. It's just something a little different you haven't seen before. All right, last little bit, C. Find the parametric equations representing the acceleration of the particle, and then find the horizontal and vertical components for the acceleration at t equals 1. They're all about this t equals 1. Well, acceleration is just the derivative of velocity. So a of t equals v prime of t, right? Just like it always has. That doesn't change. So take the derivative of velocity. If you go back and look, that was, what was that? 3t squared plus 8t, so that's going to be 6t plus 8. Take the derivative of the y. That's going to be, it was 4t cubed minus 3t squared. That's going to be 8t squared minus 6t. I'm sorry, 12t squared times 3. 12t squared minus 6t. And we want to know what that's doing at 1. A of 1, plug a 1 in. 6 times 1 is 6, plus 8 more is 14. There's your horizontal movement. If I put a 1 in here, I get 12 minus 6. That gives me 6. That's your vertical component, and there's your answer. That's your acceleration at 1. All right, last one, and you're saying, thank God this is taking forever. Find the distance the particle travels from 2 to 5. Well, the distance the particle travels, go back to your big old chart there, distance is the one that's the integral. Distance is the integral from a to b, in our case 2 to 5, of this big old square root that we did. This guy is, I'm going back to first derivatives for this, so 3t squared plus 8t, quantity squared, plus 4t cubed minus 3t squared squared, and that's with respect to t. So the deal is you go to your handy-dandy calculator and you put that in your handy-dandy calculator, and lo and behold, it comes out to be 536.462. And my friends, you have just completed all of 6-1. Now, as far as h-dubs goes for these guys, there are a couple that I'm making optional because it just gets to be too much, and I'm trying to keep things somewhat reasonable for you. First optional one is 2b. And this is, you can see this when you see the what I posted online, but 2b is optional. And the other one that's optional is 3c. 3c. This one, see how it gets into ln's of secant? You don't need to go that far. This guy's optional as well. The rest are all good to go. I can tell you the one that most interests me is number 7. And the reason why it does is because this one is a lot like an AP exam question. So knowing how to do that one is probably pretty important. All right, there you go. Shoot me an email if you've got any questions. I'll see you in class. Thanks for all your hard work. You guys are the best.